So to understand the periodic trends in effective nuclear charge, you've got to understand that there's a difference between core electrons, which are not involved in bonding, and the valence electrons, which are the electrons that are lost when you form a cation or gained when you form an anion. Okay, so the core electrons are situated in between the nucleus, where all the positive charges are, and the valence electrons, which are negatively charged. So the more core electrons you have in between the nucleus and the valence electrons, the less of the nuclear charge those valence electrons are actually experiencing. So there is less electrostatic attractive force holding those electrons as part of the atom. So they're experiencing less effective nuclear charge. So we are able to then derive other properties such as atomic radius from that, because the less tightly those valence electrons are held, the more diffuse and spread out they'll be, so the larger the atomic radius is. And likewise, ionization energy is going to decrease in terms of cost, because remember it's a positive enthalpy value, so it's endothermic cost energy. So a smaller number means it's more energetically favorable for ionization energy, and a bigger number means it costs you more energy. So obviously the lower the effective nuclear charge, the less tightly those electrons are held, therefore the less energy it takes to remove them for the first ionization. So there's actually, if you're more of a math brain person, there's an equation that will help you with this, that the effective nuclear charge equals the atomic number, which is the number of protons in the nucleus, minus a shielding constant, which is equal to the number of electrons in the core electronic configuration, okay? So essentially, we'll help you to predict this trend, okay? You can probably imagine as you go across a period that the shielding constant is going to stay the same. Let's pick period 2 between sodium and argon, for example. Sorry, period 3. Can't count this morning. Between sodium and argon, the shielding constant is going to remain constant. That neon is the core configuration. If you was going to write the electronic configuration for sodium, you'd write neon in your square brackets and then 3s1, for example. So that core configuration of 10, the neon configuration, is going to remain constant all the way across period 3. So going from like sodium to argon, as you go across, you're increasing Z by 1 each time, okay, because we are adding a proton, therefore we're adding an electron, but as you go across S, the shielding constant is remaining the same. So the effective nuclear charge is actually going to increase going across a period because you're adding more protons and more electrons, but the shielding amount is remaining constant, so the effective nuclear charge experienced by each electron you're adding is actually increasing. So that's going to do two things, right? That's going to cause the atomic radius to decrease because they're being held more tightly, they're being sucked in more, and it will cause the ionization energy to increase going across a period because an electron that's held more tightly is going to be more difficult to remove, which is why you don't see any cations being formed on that right-hand side of the periodic table because the ionization energy is too high. Okay, that's why they form anions instead. All right, so let's pick on this nickel, iron, vanadium, scandium. I would predict effective nuclear charge is going to increase going across the period. So out of these guys, I'd expect nickel to have the highest effective nuclear charge. So let's just quickly do the math. If you're more of a math person and you not quite so comfortable reasoning that out, and make sure that the math agrees with what we're expecting. So Z and S minus S from Z, and you'll get your effective nuclear charge. So remember what we predicted. We predicted that nickel would have the highest effective nuclear charge, and therefore out of these guys, scandium would have the lowest. So Z of nickel is 28, Z of iron is 26, vanadium is 23, and scandium is 21. So they all have the argon and then 4s2 3d blah configuration. Okay, so S, the shielding constant, is going to be the same for all these. So the argon configuration represents those 18 core electrons, which are having nothing to do with any activity, reactivity, etc. Okay, so we're going to subtract S from Z, so our effective nuclear charge for nickel is 10, then iron will be 8, vanadium will be 5, and scandium will be 3. So confirmed with numbers, the effective nuclear charge is going to be highest for nickel, so that supports our trend. So let me just summarize that for you with a visual representation that as you go across a period, your S is constant, your Z increases, so your effective nuclear charge increases. Okay, so I had a little look through the questions, and I didn't see any talking about going down a group. So let me just point that out for you real quick. Oh, that arrow's not really where I would want it, and I can't move it. Whatever. It's a bit closer. So as you go down a group, what is happening as you go down period 1, 2, 3, that corresponds to quantum numbers, n equals 1, n equals 2, n equals 3. So you're adding shells of electrons further and further away from the nucleus. So do you think that the valence electrons in n equals 5 shell, for instance, would experience more or less shielding than the valence electrons in an n equals 2 shell? Well, you'd be right. There's a lot more shielding between the n equals 5 electrons and the n equals 2 electrons, right? Because there's just more stuff in between those outer valence electrons and the nucleus, okay? So as you go down a group, n increases, like literally the number of shells. Therefore, the outer electrons are further away from the nucleus. There's more shielding in between them. So our shielding is increasing, which means that our effective nuclear charge is going to be decreasing, okay? And we see that in like reactivity. If you've ever seen anyone demonstrating like dropping group 1 metals into water, like lithium, sodium, potassium, etc., you'll see that the reaction gets more and more violent as you go down the group 1, and that's because those valence electrons are not going to be held as tightly to the nucleus because there's less effective nuclear charge. So radius is getting bigger, ionization energy is getting smaller, so reactivity increases. Okay, so I just wanted you guys to see that.